Hello everyone, welcome back to Learning at 11th hour. Today we are going to discuss a few problems on Thevenin's theorem. In this problem, we have a combination of a current source, a voltage source, and a dependent voltage source, which is voltage controlled. We need to compute the load current I flowing through the 2 ohms resistor and also obtain the Thevenin's equivalent circuit. So, in order to do that, the first step is to identify the output nodes. So, if 2 ohms is the load resistor, AB is going to be the output terminals, uh, and I is going to be the load current. Now, we can open circuit the 2 ohms resistor, which is the second step. So, in that case, we would obtain the circuit as 10 volts with V naught in this manner in this 1 ohm resistor, 1 amp current source. This is the dependent voltage source and the open circuited terminal AB. Once we've removed the the load, we can compute the Thevenin's voltage or the open circuit voltage across AB. Now, looking at this particular circuit with the open circuited condition, we see that there is a current source in between this mesh with the current I1, loop current I1. And this could have been a potential loop, but now that it's open circuited, we can just assume that this is a voltage drop VTH available over here and apply the super mesh in this manner for this entire circuit, ignoring the current source. So, if we apply super mesh with KVL, what we get here is marking the drop directions in this manner, we get minus 10, and the direction of V naught opposes the dotted direction that we have assumed. So minus V naught, and here we have a voltage drop of plus 3 V naught because this arrow and the dotted arrow is in the same direction. So plus 3 V naught, again plus VTH is equal to 0. So here we get uh, 2V naught plus VTH is equal to 10. Now, if we look at this circuit closely, since this part is open circuited, the current that comes out from this 1 amps current source cannot flow in this direction because it is open circuited. So there is no path, a complete path available for the current to flow there. So the entire 1 amps will flow into this 1 ohm resistance. Therefore, I can say that V naught is nothing but 1 ohms into the 1 amp current from the current source, which is nothing but 1 volt. So now if we replace this V naught in this first equation, what we get is 2 plus VTH is equal to 10, or VTH is equal to 8 volts. So this is the next step. Now the next step is to compute RTH. So we need to find out the Thevenin's equivalent resistance across the open circuit terminals. And in order to do that, we need to first kill the sources. Now, in order to compute RTH for a circuit having dependent sources, we need to apply the test source method. So, what is this test source method? So here what we are going to do is all the independent sources are going to be killed, where the independent voltage source is going to be short circuited and the independent current source will be open circuited. But the dependent source is going to remain in the circuit. So now let's first achieve that. So we are now going to short circuit this 10 volts source. Then this is the 1 ohms resistor, and we are going to keep the 1 amp current source open circuited. So there's going to be no element in this branch, followed by the dependent source connected in this manner. Let's keep the V naught as it is, followed by the terminals A, B, across which we need to find the Thevenin's resistance. So here we are actually retaining the dependent voltage source. Now, how do we compute RTH? So if we are able to find out the voltage across AB terminal, say VAB, in this scenario, right, which is not the same as VTH, because here we do not have the 10 volts and the 1 amp available, right? So if you are able to compute VAB for this particular scenario, and we are able to divide it by the current, say I, flowing through it, that should be equal to RTH, isn't it? So if I am going to assume that I'm connecting a test source of, say, 1 amps in this direction, so then I in this case is going to be 1 amp. So this is 1. Now if I apply KVL in this loop, then I will be able to find out VAB2. So how do we compute KVL? So this is the drop direction. Here let's apply KVL here. So if this is my plus and minus, so we have minus VAB, and we have minus 3V naught and plus V naught is equal to 0. So now what we get here is, we get minus 2V naught is equal to VAB, and V naught is equal to nothing but 1 ohms into 1 amp. So therefore this is nothing but 1. So we get VAB to be equal to 2V naught, which is minus 2V naught, which is minus 2 into 1, which is 2 volts. Minus 2 volts rather. So now when we compute RTH, we just take the magnitude of this, right? So we have 2 divided by the current I, or we can consider that we have assumed the direction of I to be in the opposite way. So if we would have considered the direction of the 1 amp source to be in the clockwise direction, in that case we would have actually got the value of VAB as plus 2 volts. Anyhow, resistance cannot be negative, so here we get RTH to be 2 ohms. So this is called as the test source method, wherein we have actually connected a 1 amp test source in order to compute RTH. So finally what we have is, we have VTH is 8 volts and we have RTH is equal to 2 ohms. So we can draw the Thevenin's equivalent circuit as VTH, which is 8 volts, in series with 2 ohms, with the load resistance of 2 ohms connected with it. So now I is nothing but VTH by RTH plus the load resistance. Here in this case it is 2. VTH is 8, RTH is 2, and the load resistance is also 2. So we get the current I as 2 amps. So having understood this problem, let us now look at two other problems asked in the doubly paper from GATE. So this particular problem was asked in the year 2021 in the doubly paper. Here we need to compute the equivalent Thevenin voltage and the Thevenin resistance across terminal AB. So let's compute VAB. So in order to do that, so we see that this 5 amps is going to flow only into this 10 ohms resistor because there is an open circuit over here. So it's not going to enter into this. So therefore, this particular voltage drop is nothing but 50 because I1 is 5 and this is 10 ohms. So 5 into 10 is nothing but 50 volts. So this drop is 50, with this being positive, this being negative, and this being the direction of the drop. Now, if I want to compute VAB, I can apply KVL in this particular loop. So if I consider that there is no current flowing in this 2 ohms resistance, so there's not going to be any voltage drop over here, but this 3I1 is going to be there with the drop direction in this manner, where I1 is nothing but 5 amps as seen over here. So therefore we can say that there is going to be a voltage drop of 50 in this 10 ohm resistor, and this particular dependent source is going to have a value of 15 volts in this direction. Therefore we can find out that VAB is nothing but so applying KVL, if this is plus minus, I can say that let me assume this to be my direction. So minus 50 minus 15 plus VAB is equal to 0. Therefore, VAB is nothing but 65 volts. So therefore, the Thevenin's voltage over here is nothing but 65 volts. Now, in order to compute the Thevenin's impedance across the terminal AB, so we see that there's a dependent source over here. So therefore, we need to use the uh, test source method. So what do we do now? This 5 amps is an independent current source. So therefore, I can open circuit it. So I'll just keep the 10 ohms resistor over here, followed by this 3I. This is the dependent source, followed by the 2 ohms. And these are the terminals A, B, across which I am going to connect a 1 amp test source. So therefore, this is the current which is circulating in this loop. So let me now again go for applying KVL, this being the drop directions. And what we obtain here is, if we are able to find the voltage VAB and divide it by 1 amp, then I will be able to get RAB. So that is the idea here. So what really is VAB, considering that this is plus and this is minus? So this is the direction of drop of VAB. So applying KVL, what we get here is 2 into 1 amp, and this one is plus 3I, and this drop is plus 10 into 1 amp, and here I is nothing but 1 amps because we've considered the test source to be 1. Therefore the current flowing through 10 ohms is 1 amp, which is nothing but I1 in this case. So therefore this put together should be equal to VAB, or I can say minus VAB is equal to 0, and then arrive at this equation. So therefore VAB is now equal to uh, 15 volts. In order to compute RAB, I'm going to divide VAB by 1 amp, which is the test source that I've considered. So 15 divided by 1 ohms, which is 15 ohms. So therefore, we obtain the Thevenin impedance to be 15 ohms, and the Thevenin's voltage here is 65 volts. Let's move on to the next problem. In this problem, we've been asked to compute the Thevenin's voltage VTH across the two terminals as shown. So let's mark this as terminal A and terminal B. Now, we know that the current from this 5 amp source is not going to enter into this 3 ohms resistor because these two terminals are open. There is no closed path for current to flow in this direction into this 3 ohms. So therefore, whatever current is coming out from this current source will enter into the 2 ohms resistor over here. So if I mark this to be plus and this to be minus, this will be the direction of drop. And since we know the value of current entering the 2 ohms resistor, we can obtain the drop value over here as 5 into 2, which is 10 volts. So this drop is 10 volts. Now, let's look at the drop across the 3 ohms resistor. This 3 ohms resistor is connected across this 4 volts voltage source. So therefore, whatever voltage is uh, appearing across the voltage source will also appear across the 3 ohms resistor. So this being plus and this being minus, the voltage drop across the 3 ohm resistor will be 4 volts. We now need to compute VTH. So we've been given that this is plus and this is minus. So now if we consider this entire super mesh, ignoring the 5 amps, and we apply KVL at this super mesh, so here we would be able to obtain the value of VTH. So let's begin. We can say that the direction of the assumed arrow here and the drop 4 volts is opposing each other. So we get minus 4 volts and minus 10 plus VTH is equal to 0. So therefore, we get VTH is equal to 14 volts. So this is the solution to this particular problem. So I hope this video was helpful for you all, and following this video closely would have boosted your confidence in solving problems from GATE. So the problems might appear complicated, but they all need application of very basic concepts. So it will come intuitively with practice. Please keep watching this channel and subscribe to this channel for more such videos. Thanks for watching.